Welcome to video module number 1, Introduction to GIS and Geospatial Data Models. My name is Matthew Toro. I'm the Maps and Imagery User Services Coordinator at the GIS Center at Florida International University. I'll be your guide in this short, primarily conceptual video module. Let's start by asking ourselves, what is a geographic information system? Here's a good textbook definition provided by ESRI, the Environmental Systems Research Institute. A geographic information system, GIS, integrates hardware, software, and data for capturing, managing, analyzing, and displaying all forms of geographically referenced information. That was a great textbook definition. Here's an analogy I came up with to help better understand the three fundamental functions of a GIS. GIS as a three-legged stool. The first leg of our GIS stool is digital cartography. Using computers to create maps is often the final step in a comprehensive GIS workflow. However, GIS is far more than merely making beautiful maps and renderings of two-dimensional and three-dimensional space, although that's certainly a potential of the technology. If we merely wanted to do digital cartography, though, most graphic design platforms offer the necessary functionality. What we're doing with GIS is different than graphic design, although the latter has a very powerful role in successfully communicating information. That leads us to the second leg in the proverbial GIS stool: data storage and database management systems. GIS is indeed different than graphic design because a GIS not only makes representations of geographic space, but it also stores valuable data about the objects and phenomena that constitute that geographic space. GIS offers tools for disentangling some of the interactions among those spatial patterns and phenomena. Not only does a GIS record where in geographic space things are, but it also stores qualitative and quantitative attributes and other data about those things. We extract meaning from and add value to those data by exploiting GIS technology for its most powerful set of functionality, its capacity for the third leg of our GIS stool: spatial analysis and geostatistics. Spatial analysis involves the techniques used for exploring the interrelationships of geographic data based on their topological, that is, geometric, or geographic properties. Some basic questions that can be solved through spatial analysis include, for example, how concentrated is poverty throughout the neighborhoods of Miami? And what other socio-environmental factors produce these spatial patterns of poverty? Which route is the fastest for moving bus number 72 through the metro region? What is the current habitat of invasive species in a marine ecosystem? Where is the best site to build a new public school? What is the projected land use of this particular set of land parcels in 15 years? Where is the source of groundwater chemical pollution? As you can imagine, the role of a GIS spans virtually every academic discipline and economic sector involving any sort of geographic or spatial inquiry. Here we see a great image from Directions magazine highlighting some of the uses of GIS technology, from incident mapping to transportation modeling, resource exploration, to epidemiological spread or diffusion analyses, to landscape or geomorphological analyses of topography, to demographic analysis, site selection, and land management. The number of applications uniquely suited to GIS analysis is virtually limitless. So, now that we've gained some exposure to a sample of what can be done with and through a GIS, let's talk about some of the components of a GIS. In the field of GIS and GI science, there are 5, sometimes 6, commonly identified components to the system: people, hardware, software, a network, data, which, as emphasized, is almost always the primary factor determining the particular type of analysis that can be performed, and procedures or workflows, sometimes referred to as applications. The remainder of this module will focus on geospatial data. So let's talk a bit more about geospatial data models. A data model is a mathematical construct for representing real-world objects as data. A data model depicts Earth and Earth-based objects in a manner that a computer can interpret for visualization and analysis. Source: ESRI. There are two main geospatial data models, the vector and the raster data models. The vector data model is a geospatial data model that depicts the Earth-based objects by way of three elements: geometry, attributes, and location. The raster data model is a geospatial data model that represents geography as a continuum by means of a regular grid of cells that store values for attributes. Location is implicit in the arrangement of the grid cells. Let's learn a little bit more about each of these data models, starting with the vector data model. The vector data model consists of three main geometry types: points, lines, and polygons. Vector points. Points define discrete locations of geographic features too small to be depicted as lines or areas. Depending on the scale of the map, points can be used for representing features such as fire hydrants, cities, addresses, trees, wells, businesses, incidents, etc. Vector lines. Lines represent the shape and location of geographic objects too narrow to depict as areas. Lines are also used to represent features that have length but no area. Depending on the scale of the map, lines can be used to represent features such as street center lines, rivers, power lines, ski lifts, bus routes, sidewalks, etc. Vector polygons. Polygons are bounded, enclosed areas that represent the shape and location of homogeneous features. Depending on the scale of the map, polygons can be used to represent features such as census and other administrative units, land use, land cover areas, zoning districts, etc. Alright, so let's have a little quiz here. 4 vector layers are present on the map to the left: school sites for Miami-Dade County, municipalities for Miami-Dade County, bus routes for Miami-Dade County, and the urban development boundary in Miami-Dade County. Each of these layers belongs to which vector geometry type? So, our Miami-Dade County school sites are point features, our municipalities are polygon features, bus routes are represented as line features, and our urban development boundary, or UDB, is also represented as a vector line feature. We've now seen the 3 main geometric forms of vector data. If you recall though, vector data depicts Earth-based objects by way of geometry, attributes, and location. So while we store vector features as points, lines, and polygons, we also store descriptive information about those features as attributes in an attribute table. It is here that we see the first 2 legs of our stool, digital cartography and data storage systems, in action. Our vector geometries store information about geometry and location, while our attribute table stores our attribute information in dynamically linked attribute tables. In this slide, for example, you see a set of polygon features representing all of the world's nation-states. Those nation-state features meeting a particular criterion, namely that they belong to the sub-Saharan region in Africa, as defined by the World Bank, are highlighted or selected. By linking geometry features to their attributes, not only can we map geographic entities, but we can also begin to organize and analyze these entities based on the descriptive information associated with them. The raster data model offers a fundamentally different method to store geographic data. In its simplest form, a raster consists of a matrix of cells, or pixels, organized into a grid of rows and columns. Each cell contains a value representing information. Examples of raster imagery datasets include aerial photographs, satellite imagery, digital elevation models, scanned paper maps, etc. Here we see some examples of raster imagery data. Orthophotography is great for creating base maps and to use when digitizing vector features. Raster imagery can also be used to define classes of land use or land cover. The concentration of a particular geographic phenomenon is often mapped with raster data in a so-called heat map. Slope and elevation are two topographic properties frequently modeled with raster data. Population and other socio-demographic and socioeconomic values can also be mapped using the raster data model. Some geographic objects are better suited to representation via a particular geospatial data model. Neither the raster nor vector data model is superior or inferior to the other. Rather, one data model may simply be more appropriate to use for the particular analysis one wishes to perform. This image from Oregon State University highlights some of the representational differences between vector, discrete, object-based data, and raster, surface, pixel-based data. Here's a great table, adapted from ESRI, that explains some of the characteristics of one data model versus the other. In terms of data volume, the vector data model is compact, while the raster data model is comparatively large. Raster data files are generally larger in size than vector data files. The actual structure of vector data is comparatively more complex than that of its raster counterpart. Vector data can store explicit topological relationships and rules. Raster data cannot. Vector data resolution is determined by the precision of its coordinates. The spatial resolution of raster data is determined by the size of its pixel. In terms of advanced statistical analysis, the relatively simple structure of raster data lends itself well to advanced analyses, while such analyses are relatively more difficult to execute with vector data. Because of the relatively high data volume of the raster model, it usually takes longer to manipulate and perform analysis upon. Vector is comparatively faster in terms of performance and responsiveness. That brings us to our final slide in this module regarding GIS data layers, or layering. When imported into a GIS software environment, both vector and raster datasets can be referred to as layers. Each vector or raster layer contains a related set of objects or a particular theme of data. In fact, the terms layers and themes are essentially synonymous in a GIS context, although the latter is used less frequently than the former. Because all geospatial data have an explicit connection to a particular location in geographic space, we can overlay data that correspond to the same particular location. This is where the third leg of our GIS stool, our most value-adding leg of the GIS stool, begins to present itself more clearly. By overlaying various layers or themes of data, we can begin to identify patterns and trends between and among our datasets that we might not have otherwise identified. By layering geospatial data together, we begin to add value to our data and enter the world of geospatial analysis. Thank you for watching this first video module on Introduction to GIS and Geospatial Data Models. Feel free to contact the FIU GIS Center through any of the information listed on the screen. And be sure to check out the next module in this video series on geospatial data formats. In that video, we'll take a more practical look at geospatial data by identifying some of the common file formats one should look for when collecting geospatial data.